All right, so we're going to continue with our discussion from last time, which was on functions and pass by reference. And briefly, we started to identify some error conditions that could occur when you call a function. And so that's going to be the topic of the next module, which is error handling. So to review a couple of the things that we looked at last week, and also to refresh our memory of those types of error conditions, let's reconsider the program that computes quadratic roots. So I've already taken the liberty here of modularizing this. Remember that we had three functions. The first two functions, one of the purposes of defining a function that passes things by reference means that you're passing those buckets, and means that the function can fill those buckets with values, in particular with pass by reference values, right? Root 1 and root 2. And the reason that we wanted to do this is because we actually wanted to compute two roots, and we wanted to return two values, but you can't do that. Functions only ever return at most one value. So what we did is, in our first attempt here to illustrate this, is we had a function that took a, b, and c, and it computes the roots of the first root for a quadratic equation, right? Negative b plus minus, those are the two roots. So this one was the plus, and then this one was the minus part of that. And so we'd have to split that out into two different functions. What we did instead was we created another function here that took three values, again, all by value here. So we're passing in the coefficients of that polynomial. And then we're dumping the two roots into two different variables that were passed by reference. Remember, what is this thing called? It's a pointer, right? It's a pointer to a double value rather than returning a double value. Because up here, you're only allowed to return one value, and therefore we need two functions. But down here, we can effectively return two values because I'm passing those two values by reference. I've modularized this by pulling these prototypes out into a header file, and I've got the actual definitions over here. Remember that this is the plus root, and this is the minus root for the first root and second root. And then here, we've got the compute roots, which again takes a, b, and c, and root 1 and root 2, and it computes both of those roots at the same time. Why did we have a star in front of this root here? Remember, root 1 is a pointer variable. So how do we take a pointer variable and turn it into a regular variable so that we can put the result of this equation into it? We have to dereference it. Root 1 is a reference. By putting the star in front of it, you're dereferencing it and making this thing into a regular variable so that you can put a value into it. Right? And then we ultimately return. Do we return anything yet? No, because, well, originally I returned a value. I don't need to do that anymore because you gave me two buckets. I can fill those buckets and give those buckets back to you because it's all passed by reference instead. Okay? Now over here, I separated it out into another program that I'll read these command line arguments, A, B, and C, so that we don't have to keep editing and recompiling and everything all together. And then we call compute roots here. Now there is an error here, but I want to do this as a reminder of how to compile. So I've got all these files here, roots.c, roots.h, and then root demo that uses them. How do I compile this roots.c and roots.h together? What is the flag that allows me to do that? Remember? C, because compile without linking into a main program. GCC roots.c. And when I do that, it was already created. I already did it at one point. Roots.o. That is an object file. Roots.o. It's a 64-bit object. Again, it's just a bunch of binary. Right? We're not going to be able to see what it is. Right? There's some stuff in there that you can interpret as text, but otherwise it's pretty much binary. Okay? Now that does not produce an executable program. Once we've got this .o file, we can go ahead and compile everything together. Roots.o, compile that together with rootdemo.c. Right? And this is how you compile, but there's going to be a problem here. Error, passing double to parameter of incompatible type. So let's go back over here and realize what we were doing over here. What kind of variables are R1 and R2? Are they pointer variables or regular old variables? They're regular old variables. Does compute roots here, does it take root 1 and root 2 as regular old variables? No. So I need to make sure that these are compatible. It expects a pointer variable. So how do I take a regular old variable and change it into a pointer variable, the ampersand, right? Remember, the ampersand and the star are opposites of each other. This is the referencing operator, and the star in front of a pointer is going to be a dereferencing operator. And now when I make sure to save, and now when I do this, it's happy about it. And it can actually produce this a.out. So let me go ahead and try the roots of, I'll make b large, so 1, 2, 1. Right? And the roots of 1 times x squared plus 2x plus 1 are -1 and -1. So the same root with multiplicity. Okay? Now, how can I break this program? And this is what you tried to do last week and what you're trying to do on your current hack that's due tonight, and that you'll try to do on the next hack as well. When you're testing software, that is your opportunity to try to break it. You do want to break software because and hardware. You want to stress test everything, right? When you've created a steel beam, or when you manufactured a steel beam or something, or you want to have a stress test and you want to try to break it. How much weight can this hold, right? And then once we know that, well, okay, once it's designed for a certain amount of weight and we test it to see, yes, it can hold that much weight without stress much, so it passes the test. Software is the same thing. You want to unit test it. Given a unit of software, usually a function, you want to put it through its rigors. You want to break it. So you design as many test cases as you can to try to break it. Bad inputs, inputs that are out of the range, corner cases, edge cases, all these kinds of things that you want to break your software. So help me out here. What A, B, and C will help me break this software? C, make C large, all right? Why? 1, 1, and, I don't know, 50. How will that break this? It'll create complex roots, right? Imaginary roots. And I did, in fact, break it. Nan and nan. What was nan again? Not a number, right? Or grandma, all right? All right, so I broke it that way. So maybe I want to handle that case a little bit differently, okay? What else could I do to break this? Make it 0, 1, and 1. Okay, let's make it b large. So we don't get a complex root here. How is this going to break it? Divide by 0 in the quadratic formula, right? And now I get nan and -inf. I get a different output here. I'm putting it through its stresses. I'm finding test cases that are going to fail, right? So that's the theme of today. What do we do about that? Okay. Oftentimes, programs may have always have potential for errors. Right? Some errors can be unexpected. Right? So, for example, are you expected to write software that can withstand somebody coming along and kicking the power out, or a bomb that blows everything up, or there you can go with redundancy, and that's hardware kind of stuff, where it fails over to another service center that's halfway across the globe or something like that. But you're not going to be able to test for everything. You're not going to be able to anticipate everything that could potentially go wrong. So that's why we say that programs always have potential errors, and it's never going to be 100%. You're trying to for what's called code coverage. You're trying to create as many test cases that give you, say, a 99% certainty that this software is sound and correct. You're never going to reach that 100% because there are some things that you cannot write contingency plans for. Right? Some errors can be unexpected. Many errors, however, can be anticipated. Right? We can anticipate that somebody would give us negative values or 0 or values that would lead to a complex complex roots, etc. Right? So what do we do about this? We can anticipate and write code to handle those errors. Right? Or we can let those errors be fatal. Right? And that's kind of what you've been doing in some of your programs up to this point. If a user mashes the keyboard and gives you some bad values, values that exceed 90 degrees or 180 degrees, or negative values for balances or for interest rates or something like that, you can echo an error message and immediately quit on them. try again, enter something better. But that's not always going to be the case, because the vast majority of software is not written to interact with a human. It's written to interact with another piece of software. You write one piece of software that interacts with another piece of software. So you need to be able to anticipate the errors that one software could be giving to another piece of software and then communicating those back and forth. Or you can let those errors be fatal and then and kill the entire program. Okay? So what do we do about it in, say, C? In C, our general, let me give some more room here, strategy will be what's called defensive programming. Okay? And what that means is that we will identify errors, identify potential errors, right, that could cause problems, right? And then we write code to look before you leap, right? That is, that code will check for those error conditions before it performs potentially dangerous operations. For example, division by 0. If I've got a divided by 0 and I want to compute a divided by 0, I'll look and see, well, is b 0? And if it is, I don't want to a divided by 0 because that would lead to a negative int for maybe some fatal error or blowing up the computer or something like that. I don't want to do that. I want to look before I leap. Am I about to do something illegal like dividing by 0? And if so, I don't do it. If I'm okay, if I look before I leap, yeah, I'm not going to jump into a hole, then go ahead and do it. But if you're about to do something illegal, you don't do it. You stop. And instead, you, in some way, report an error back to the calling function. We're going to do this at the function level. I'm going to call a function and give it inputs. Those inputs could potentially be bad and cause errors inside that function. What that function is going to do is it's going to look before it leaps. Am I about to do something wrong? And it doesn't do it. Instead, it immediately returns back to the calling function and communicates, wait, you gave me some bad inputs there. You're going to decide what to do. Right? And then at that point, the calling function can decide, okay, well, I'll give you better inputs, or I'll go ahead and make the decision to kill the program, or I'll reprompt the user for something, or whatever you want to do in the event of an error. That's where you handle it, in the calling function, not inside the function. Okay? The way we'll do this is through error codes. Right? Now that we have pass by reference functions, we don't need the return value. Right? And for that, I'm going to go back to my roots.c here and take a look again at this compute roots that passes root 1 and root 2 by reference. Right? By not returning a value anymore, we freed this up. It's a void function. What I can do now is I can use that return value to communicate an error. No error, or this type of error, or this type of error, or this type of error. If I've identified 5 different types of error, I can return a different value that indicates each one of those types of errors. Right? And that's going to be our general strategy. Right? We can now use the return value to indicate an error code. Right? Usually it's always an integer to indicate the type of error that was encountered. Right? And we're only able to do this because we're computing the real return value through a pass by reference function, or a pass by reference value instead. Okay? Through a pointer, and we don't have to return anything anymore. Okay? In general, you do not echo, that is, print an error message in a function. Right? Think about a typical function that you would call. In fact, think about a function that we call in the demonstration here, square root. If you pass in a negative value to square root, does it go printf? I can't handle negative values. Right? Does it pollute the output of your program that way? No. Why? Well, because it does error handling through a different mechanism. Right? It reports the error, but it doesn't actually print out a message. In addition, you do not make most errors fatal. All right? That is, you do not call exit, say 1, on everything. Right? You don't want those errors to be fatal. Square root. If you call square root on -1, does it quit out of your program? Did it quit out of our program? No, it reported a value. It reported not a number or negative infinity. Instead, it did error handling using a different mechanism, and I'll show you that in a second here. Okay, so that's that's how we're going to work it. So, as an example, let's redesign the roots demo to use error handling. Right? So let me come back. It's in the same window here. Let's go back over to roots here. And instead of returning nothing, we're going to return a value that indicates the type of error that was encountered. Usually it's going to be an integer, so I'll just go ahead and make this an integer. And over here in roots.c, I will go ahead and change that to an integer. So what are the potential errors? We've already identified a few. What's 1? Divide by 0. So if a is equal to 0, then I'll return some value here. Right? Else if, now what was another error? What I'm doing here is I'm looking before I'm leaping. That if a is 0, I don't do the potentially dangerous code down here. Instead, I immediately return an error code without having done the operations down here. We'll go ahead and come back to what this is in a second. What was the other type of error that we looked at? So b squared minus 4ac is less than 0. Or you can go ahead and put that on the other side and solve for whatever. In other words, if we've got, does anybody remember what that's called? B squared minus 4ac? It's the discriminant. Good job. It's called the discriminant under that square root. And so that's the discriminant. If the discriminant is negative, then we know that we've got imaginary roots. So I'll return, I don't know, something else. Else if, what's another type of error that we could encounter here? Remember Bret Hart. What did he tell you to remember? An invalid pointer, right? So what kind of invalid pointer could we have? If root 1 is null, or if root 2 is null. Then we don't dereference it, right? Don't dereference a null pointer, and we return something else. Otherwise, I could put an else statement here, else, and then do all this stuff here, and I'll go ahead and put it all into an else statement. Okay, and that's pretty good for now. You could probably think of some other errors, but I think that that's all that I can think of at this point. So let's discuss. What should I return here? I just need to communicate some sort of an integer to indicate an error. 1? All right, good enough. Well, as long as we're counting, what should I return here? 2, okay. And 3, okay. What about right here? No error. 0, all right, why did you go to 0? What else is 0 in C? False. So was there an error? 0, no, false, there was not. Was there an error? 1, true, yes there was. 2, true, yes there was. 3, true, yes there was. So following that pattern, you see why the C also uses 0 as false and 1 and anything else as true. Because was there an error? Well, all 3 of these conditions indicate a different type of error, but all 3 of them indicate that in fact there was an error. Okay? That looks good. So let me go ahead and recompile that. GCC, remind me what was the flag again? C for roots.c. All right. Up. Now that I'm including null here, what else do I need to include? stdlib.h, at least on this. All right. Order generally doesn't matter, but usually I put that at the top. All right, now we're good. All right. It didn't know what null was. It's defined in the standard library. And let's go ahead and try to compile roots.o and root.demo.c. All right, it didn't complain. I'm surprised it didn't complain because over here now, well, it's not complaining because we didn't do anything with the value here. Right? What I can do now is I can recapture that error code. Error code is equal to this. And now if I ran it like it is right now, of course, I would still have all the same problems as before, right? Oops, a.out, 0, 4, and 1, right? Oh, no, now I don't have the same output here because I'm looking before I'm leaping. I'm not doing these dangerous things on line 26 and 27. So it still has the old values. So what I need to be doing is I need to be paying attention to this error code here. This is where I handle the error. Again, philosophically here, should I handle the error over here? Should I be making decisions for you about what to do when you give me bad inputs? Right? I'm the function now. I'm the compute roots function. Do I take the decision away from you? You guys are the users. I'm the library. You're using the library. Do you want a library to be making decisions for you? Probably not. Right? That wouldn't be a very flexible library. You just want the library to communicate back to you something happened. Right? And now it's your responsibility to decide what to do in that case. For example, what if we got an error code of 1? If error code is equal to 1, then we have a linear function. Right? There is only one root. And what is that root? What we have here is bx plus c is equal to 0. So what's the root? X is equal to minus c divided by b. Now we're back at square one. What happens if b is 0? What's going to happen? Then divide by 0. I won't worry about that right now, though. Okay, that's another issue. So what I'll do here is I'll decide to handle this differently. You have a linear function with solution equal to %f and the line, and we'll go ahead and compute negative c divided by b. And one of these needs to be, at least one of these needs to be a double, so I'll go ahead and typecast this one as double. And there we go. Are we good? Yep, there we go. All right. So I decided to handle that differently, right? Rather than reporting inf, nan, whatever, I'm going to actually do a different operation because I have more information now. I know that this is not a quadratic equation. This is, in fact, a linear equation, and so I'll go ahead and compute it differently. Else if error code is equal to 2. I know it was 2, but what was the second error? So the discriminant is negative. That means we've got complex roots. Okay, so I'll just go ahead and say use a complex number library. All right? And I'll refuse to even output anything. All right, thankfully you remembered what 2 was, and I didn't remember. Else if error code. Now, how many were there? I forget. I even forget how many there were. 3? Okay, so if it was 3, what was that? The bad pointers. Okay, so printf, that's kind of fatal, so I'll say bad pointers or something. Right? There we go. Otherwise, I'll go ahead and print out this message that, in fact, it worked. Right? Okay, thank you for helping remember the order of those things because I didn't. 1, 2, 3. I can't remember all that stuff and talk at the same time. So GCC roots.o and roots.demo.c. Let's go ahead and check it out and test it. So let's give it something valid to make sure that we didn't break anything here. Make b large and a and c small. Okay, or what worked before 1, 2, 1? Right? There we go. And we get the same answer as before. Generally, with test cases, you want to test the same things over and over again. That's why you build test suites and unit tests and use a framework like you're going to use on Thursday's Hack Day, where you use a framework that we've chosen, CMACA, because that makes tests predictable and repeatable. And it's not a manual process. You just compile everything, run it, and it gives you a report. I ran 10,000 test cases. You passed all of them except for this one over here, and you need to take a look at that one. Right? What else should we test? 0 to 1, say. What message should we get back on this one? You have a linear function with solution. Oh, OK, great. All right, now I'm getting useful information out of this program. What was the other one that we should test? Small b, so 2, 0, 2, let's say. Yeah, using the complex number library. Now, I'm not going to be able to force, at least from the command line, the way that I've done this, I'm not going to be able to force one of these things to be null. But of course, I could try doing something like this, where I pass in, I come back in and I manually pass in null. And you could do this with a testing library to force it to take a null value and see if it breaks it. Let me go ahead and go all the way back up here. Give it something that is legitimate. 1, 2, 1. Right? And bad pointers or something. OK, so I've tested all that. And again, what you want with testing is code coverage. I've tested pretty much every possibility that we identified. And you can also do what's called fuzzing. So there might be some things that you haven't anticipated. So let's just go ahead and randomly try to break it by running 10,000 random values. We'll try to ram 10,000 different values into this and see if it dies somehow. Right? Sometimes they call it chaos testing. It's usually called that's the new in word of calling it, but it's really just fuzzing. You try to fuzz it with fuzzy data, badly formed data, and see if you can break it that way. Right? So let me go ahead and undo this so that it actually works. Otherwise, we'll never get another decent test case out of it. All right? And make sure that I didn't break it. Yeah, it's still good. Okay? But there is a problem here. Right? And again, I was alluding to it. Of course, I could remember 3 things. I'm not that dumb. But what if we had like 5 types of errors? What if I had 10 or 50 types of errors? Are you going to remember those? In fact, even with 3 errors, if you come back on Wednesday or a week from now or a month from now or a year from now and look at your code, right, and you just have these mysterious numbers, 1, 2, and 3, are you going to remember what those stand for without having to go back and read your original program okay, if error number 472, that was this thing over here, right? No, you're not going to remember, right? And even if you do remember, it's not at all readable to other people. These are what are called magic numbers. Where did they come from? I don't know. They're just magic. Where did they come from in this case? Well, I just started enumerating all the possible errors, and so that was 1, 2, and I just started counting 1, 2, 3, 4. There's no rhyme or reason to these numbers. They're meaningless. I could go ahead and change these around. I could change this one to 2 and this one to 1 as long as I change it over here. Right? But if I change them over here and I don't change them over here, there's a real big problem because now the error codes don't match up. Right? So what I want to do is I want to avoid this. I don't want to use magic numbers. Instead, I want to use something else. I want to use enumerated types. Right? So before we do that, though, let's take a look at how C internally handles things, how C does system-level error handling. Right? Because this, we've already identified a problem. There's magic numbers in there. We don't want magic numbers in our code because I can't read those things. It's not maintainable, and it's just a nightmare to have to read these numbers. Where did that number come from? 3 months from now, we're never going to remember what it was. The POSIX standard actually only defines 3 error codes. Right? And what is POSIX? POSIX is portable operating system interchangeability. So the X came from wherever. They added it at the end to make it sound better. They needed a snappy acronym, right? It's portable operating system interface or interchange or something like that. And the only, pretty much every operating system is POSIX compliant except for one. Guess which one isn't? Windows, right? Otherwise, Mac or BSD based, Unix, Linux, all of them are POSIX compliant. So if you've got a POSIX standard, then it's an extension of C basically, and these standards will be in all of those. although they are making improvements to Windows. I don't know, maybe it recently is POSIX compliant, but I'm not sure. So EDOM indicates an error in the domain of a function. Right? For example, the example that I usually give is square root of -1. Is square root of -1 defined? No, that's bad input. So you're going to have to remember back to your math days. What is the domain of a function? There's domain, and what's the other thing? Range, right? Domain of a function is its input, and the range is the output. So EDOM indicates, i.e., an error in the input, right? And DOM is just, E of course stands for error, and DOM is just short for domain. And then there's range, right, which indicates an error in the range of a function, i.e., the output. Right? For example, the example that I usually give is log of 0. Right? And that is natural log. That is, you could argue that that's undefined, but what value is it? What does the log function look like? Right, so it's monotone growing over here, but when it approaches 0 from above, what happens to it? Goes off to -infinity. All right, that is going to be that is not a representable output. The input is representable, and for the log function, they decided that that is valid input, except that it leads to bad output. It leads to an error in the range of a function. And the other one, the third one, is EILSEQ, which stands for an illegal byte sequence. You will never ever see this. If you see this, then something seriously went wrong under the hood, and you probably I think you could probably force this by giving it some malformed UTF or Unicode or something, maybe, but I'm not sure. All right, each one of these is defined in a header file named error no, right? .h, right? This stands for error number. Right? And O is going to be short for number. Right? In the event of one of these errors, a global variable named, well, error no for error number is set with one of the 3 possible values, right? Which you can then check. As long as you include error no.h, then you can call your math library functions, and you can check to see, was it illegal input? Was it illegal output? And then you can choose to handle those errors however you want. Right? Not that you're actually going to do this in practice, but I just wanted to show you a demonstration of how it works in C, because we're going to take a page of that playbook, and that's how we're going to do our own error handling. So what I've got here is a demonstration. It's already been set up. This is actually, you can find this in the book if you want. CSC 155E programs. Error handling. Yep, there we go. So let's just take a look at this error number demo, basically. I've included the error no.h file. I've created some variables here, a, b, c, and x. A is set to -1 because what I'm going to do is I'm going to call the square root of value on a. First of all, I call it on b. The result is I print out the result, and then I print out the error number. Predict. Square root of 2 is going to be 1.41. Is that an error condition? Is that invalid input or invalid output? No. So what value is the error number going to be? What do you think? 0. Right? Now, let's go ahead and try calling the square root value on, again, a was -1. What's the error number going to be here? I have no idea. All right? But there's certainly going to be an error, and it's not going to be 0 anymore. Okay? So what I need to do instead is I need to compare this error number to, was it an EDOM error? And I'll print it out that there was an error in the domain. Or was it an E-range error? Or was it an illegal byte sequence error, et cetera, et cetera. And then I print out a message, and we'll see what this error message actually says. Don't worry about this. Then as a third demonstration here, I call log of C. What was C again? C was 0. So what should I get out of this? What type of error should this be? An illegal range, right? So it should print out that it was an E range error. But when I print out the raw number, what do I get? I don't know. Let's find out. Right? And finally, the error message here. Right? Let me go ahead and compile this. Okay, I need to include the math library because I'm on the CSE command line. All right, and let's go ahead and run it. Bunch of mysterious numbers. So your prediction was correct. It was going to be 0 because there was no error. And the square root of 2 is 1.41 blah, blah, blah. What was the square root of -1? Well, it's not a number. In fact, negative not a number. What was the error code? 33. Do you know what did you guess that it was 33? No, I heard a few guesses out there, 1 or 2 or 3 or maybe, right? 33, why is it so high? Okay, well, fine. What about the E range error? It happens to have a value of 34. So maybe they just started their counting at 33 for some mysterious reason. I don't know, right? In fact, there was a rhyme and reason to this. And then there was a numerical range value out of range. And like I said before, I don't know how to force an illegal byte sequence error, so we're not going to take a look at that. Those aren't the only error codes. Those are the only error codes required for a POSIX-compliant system. In fact, there are many other error codes. What are they? Well, there's E-access, permission denied. There's E-bade, invalid exchange, whatever that means. Let's see, there are some funny ones in here, not intentionally funny. Let's see, E-child, no child process. There's one called dead, synonym for E-dead link. Yeah, owner died. That's the funny one that usually people think is funny at least. What's an owner? Well, anytime that you run a process on an operating system, that process is run by a user. The user ends up being that owner. So if the owner logs out or something and the process is still running or something like that, then you could end up with an E-owner dead error of some sort, right? There's E-range, right? Result too large, or it was out of range, right? Or too low because negative infinity. What else? Read-only file system, right? You can't write to the file system. Cannot send after transport endpoint shutdown. I don't know what that means, but timer expired, right? So there are dozens and dozens and dozens of these. If we simply used a bunch of mysterious numbers like 33 and 34, you'd always have to be coming back here, looking at this list, what was 33 again, what was 34 again, what was 35 again, right? And so it's not a good idea to use mysterious numbers, especially if you've got a whole list of these things. In fact, some of these are, still kind of mysterious, like EIO, input-output error. Well, okay, that's really general, but at least I know EIO, okay, well, there was an error with the input-output. These things are more human-readable. They all begin with E for error, and then a human-readable message here, intended to be human-readable, for what actually happened. The way that we've got it over here, is that at all human-readable? No. So what I want to do now is I want to take a page from the POSIX playbook on how C handles system-level error handling, and I want to introduce that here. Right? Now, there is a technical difference here. The way that they handle it is through a bunch of defines. Define E range to be 33. Define E or E DOM to be 33. Define E range to be 34. Whatever. Those are all. You can do that with preprocessor directives. But what we're going to do is we're going to use enumerated types instead. C enumerated types. Okay. Many pieces of data have a fixed and limited number of possible values. For example, errors, of course, but more relatable here immediately would be months, right? Or days of the week, or whatever, right? Or days of the week, right? Etc. So how many days of the week are there? There's only 7 of them, right? And they're not making any more right now, right? So it's a fixed value, it's small, and it's limited. So start listing the days of the week to me. What's the first day of the week? You can argue about it, but usually it's Sunday. Well, Monday. Okay, somebody did want to argue about it. What's the first day of the week usually? Sunday, Monday, Tuesday, Thursday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, right? So what did I just do? I listed them out. Well, what's another name for a list? An enumeration. And that's what an enumerated type is. It's nothing more than a list of human readable values, right? In C, you can define an enumerated type to hold human readable terms for your list of possible values. Right? As an example, let's just go ahead and do the days of the week. Now I'm in code mode here. The way that I'm going to do this is using a type def. And you can see that it's highlighted in a nice magenta, meaning that it's a keyword or a reserved word in C. What do you think it's short for? Type def. Def is definition, right? Type def, so I'm defining my own type. What type are you defining? Enum, which is short for enumeration. Right? So what is your list of things? Well, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Right? Saturday, there. All right. That's not an Oxford comma. That comma is not necessary. You don't have to put it there. You can if you want. In fact, many style guides tell you should put that last comma there because if you ever do come in and change the list and add something to the end of the list, the comma is already there and you don't make a mistake and forget one. All the other commas on lines 43 through 48, those are necessary because this is a list. You could have put them all on one line, but one line, that's not how you list a list, is it? Right? If this were a document, how would you list a list? Bullet point, bullet point, bullet point, bullet point, vertically. And that's how we're going to do it in our code here. Okay? So there is my list of things. I need to give this list a name, day of week, right? Along with a semicolon. Right? Now what this is doing is it's defining a new type of variable. Types of variables that are already built into the language include int, double, char. Right? What we've done is we've defined our own user-defined type here called day of week. Now, under the hood, it's still an integer, and we'll get to that technical detail here in a second. But essentially, I'm defining my own type. Later on in the program, what you can do, later on, ... you can define your own day of week. Day of week today is equal to, well, today is Monday, so should I set it equal to 1? It's actually the second day of the week, which would start at, because we start our counting at 0, 0, 1, 2. Well, that kind of defeats the purpose of defining an enumerated type. Instead, what should I set it equal to? Monday. Now I can use those keywords there, right? Day of week tomorrow is equal to Tuesday, right? Right? And you can have all of these things. What is today plus tomorrow? What is Monday plus Tuesday? I don't know. Have you ever thought about adding days of the week, Monday plus Tuesday? So it's the second day of the week and the third day of the week. So that'd be like Friday, the fifth day of the week, or I don't know what. I have no idea, right? But unfortunately, it's something you have to deal with in code here. So syntax and style notes. When you do this, I'll go ahead and do it like this. You use type def enum, right, which stands for type definition enumeration, right, and opening and closing curly brackets, placing the list of things, elements, I should say, in a comma delimited list, right? Generally, the name of the enumerated type uses upper camel casing, right? And the each element uses upper underscore case casing. So all of these were just single words, Monday, Tuesday, Wednesday, Thursday, Friday. But if you had multiple words, they would all be caps, and you would separate the words with underscores instead. Okay? Those are the suggested style. Of course, there are other opposing styles. For example, the styles over here, they had no underscore between the E and the other words, or key expired. There was no underscore between key expired, but two words. As long as you're consistent about it, we're not going to mind. Okay? Generally, white space doesn't matter, but all the commas are necessary, except the last, which is suggested. Right? Usually the list is one element per line, right? So a vertical list basically, and you end the declaration with the name of the enumerated type and a semicolon, because it is a declaration. So let me go ahead and go back up here and highlight that for you. This is the name of the enumerated type, day of week. It follows that upper camel casing. And then we end the entire thing with a semicolon here. Later on in the program, you can use those keywords that you've identified in this list right here. If you don't put it in the list or some other list, then it's not going to know what the hell Monday is. It's not going to know what Tuesday is. If you misspell them, it's not going to know what they are. Right? Now, unfortunately, or fortunately, it depends on your outlook, the way that how this works. Right? Internally, C assigns integer values to each element in the list, starting by default with 0. Okay, so in this case, i.e., in the example, Sunday has a value of 0. Monday has a value of 1, etc. What value does the last day of the week, Saturday, have? Has a value of, well, how many days are in the week are there? 7. So is it 7? No, you start at 0. 0, 1, 2, 3, 4, 5, 6. So it has a value of 6. Right? Consequently, you can screw up the enumerated values. You screw up enumerated variables. Right? So for example, let me go ahead and bring down, what did we have up here? I asked the question of what was Monday plus Tuesday, right? Example. Once I have that defined up there, what happens if I go day of week when is equal to Monday plus Tuesday? What is that going to be? When will have a value of ... Monday, remember it was the second in the list, so it has a value of 1. Tuesday would then be the next one, so it has a value of 2. So it would be 3. What day is 3? Sunday, Monday, Tuesday, Wednesday. So it would be Wednesday. And that's only because they were contiguous, right? What if I do when is equal to Monday plus, I don't know, 50? What value is that now? It'll be 51. Do you see 51 values in this list? Nope. So it'll be invalid. Right? But the compiler won't complain. The compiler won't enforce anything other than, well, it's just an integer, so 51, it's the 51st day of the week, right? Whatever that means, right? Or just, negative value. What's the negative 10th day, right? Again, this is invalid, right? You can test against valid values. For example, if today is equal to Friday, or no, Saturday, printf yet another game day. All right, there we go. Or maybe it's a by. All right. So you can test whether or not a given day is equal to another day. Of course, you can test to see if it's equal to 51, but that's not very useful, and it defeats the purpose of using these things. So you have to be careful. The takeaway here is understand that the actual representation is an integer, but don't treat it like an integer. So for example, you could go Monday plus 1, and then that'll get you Tuesday. Yeah, that'll work. But what happens when you roll over to Saturday, Saturday plus 1? Saturday plus 1 is not Sunday. It doesn't roll back. Saturday, which is 6, plus 1, 7. Is there a day of the week that's 7, at least in the definition that we had? No. So you'd have to do something like mod, right? You can do some basic arithmetic. For example, Saturday, or say Monday plus 1 is equal to Tuesday. This would be Tuesday. Let me actually make code here. Day is equal to Monday plus 1. This would actually be Tuesday, but day is equal to Saturday plus 1 would be invalid. So one way of handling that is by going day is equal to Saturday plus 1 mod out by the number of days, 7. And this would be Sunday. And so you can do stuff like that. You just need to be extremely careful and use it wisely. Okay? All right. Don't abuse enumerated types. So demonstration. Incorporate enumerated types in our root demo. So what I'm going to do, in general, enumerated types are defined in header files. Right? So what I'm going to do is I'm going to go over here to my header file here, and at the very top, I need to define an enumerated type. So remind me, what are the keywords again to define an enumerated type? Type def, define a type, enum, opening bracket, closing curly bracket, and we'll call it an error, there we go. Or maybe maybe we're polluting the namespace. Maybe another library has an error type as well. Our library is for roots, so maybe root error, right? Quadratic root error, something like that. Right? So what were the types that we already what were the types of errors that we've already identified? One of them was a division by 0 error. One of them was a complex root error. One of them was a null pointer error, and the other one was no error. So which one should we put first in our enumeration? No error. Why? Remember, it starts counting. It starts at 0, 1, 2, 3. By the way, you can short circuit that. You can go ahead and start your counting at 10. Now it'll start at 10, 11, 12, 13, 14, if you really want to, but generally we won't do that. So what was the second type of error again? I don't know. I'll just go with division by 0. The third type of error, maybe that was null pointer error. Division by 0 error. And the other type of error that we identified was complex root error. Right? And I went out of order intentionally there to show you that that doesn't matter. As long as you're using these designations now throughout your program, then it'll be fine. The one that I cut and paste, division by 0. So division by 0, we'll return that error now. And no error, instead of returning 0, we'll go ahead and return no error. And instead of returning 3, we'll return null pointer error. And instead of returning, the last one would be what? Complex root, thank you. There we go, complex root error. Now we can leave the return type as an integer if you really want to, but I did call my enumerated type root error, so we might as well use it. Right. Now over here, now let me go ahead and make sure that this compiles. Again, compile without linking roots.c. Oops. Okay, exit. I'm still on CSE. There, gcc roots.c. Compile it without linking. There we go. Oops. Oh, what did I not do? I didn't change it here. There we go. Root error. I didn't change it in my header file. And now it's perfectly fine. And now I can come over here into demo, and instead of looking at these mysterious error codes here, oh, a linear function, that was a division by 0 error. A complex number, well, that was a complex root error. Null pointer error, this would be null pointer error. Otherwise, and I don't have to put no error here, but you can if you, no, don't do that. Don't do this if error code is equal to, well, maybe no error, then you can do this. And then have another catch-all here, printf something really went, something went really wrong, invalid error code. Because if it's not one of these 4 that we identified, it's something else. It's -5 or it's 2000, right? And we only have 4 error codes that we defined here. So maybe that's our catch-all now here. I don't know what kind of error it was. You need to go back and fix your enumerated type here. Okay? And now when I compile everything together, oops, forgot my semicolon over here in root demo after the print statement. And maybe make it nice with an n-line character. There we go. And same stuff as before, 0, 1, 1. You have a linear function with a different solution. 1, 2, 1 to make it valid. 2, 1, 2 to make it complex. And then, of course, I can't force without recompiling null pointer error. Right? All right. That's how you do basic error handling. You don't, when you're the designers of a library now. Whenever you're writing a function, you're designing that function. If you start making decisions for the users of your function, and you are one of the users of your function, right? If you start making decisions for other people or yourself in other contexts, then you're basically taking control away from the user. You're making your library, you're making your functions less flexible. And so you don't do that. Instead, you look before you leap. You do defensive programming. Am I about to do something bad? And if so, you don't do it. Instead, you report back to the calling function, hey, you are about to divide by 0. You need to handle that. You needed to make the decision on what to do about it. You don't take the decision away from the user. Just like the math library doesn't take the decision away from you. If the math library made the decision to quit out of every single program that called square root with a negative value, a lot of stuff would break. You want your libraries to be more flexible. You want them to be expressive in that they will communicate the errors back to the calling function. And then it's the calling function's responsibility to decide what to do. Go ahead and make it fatal and delete, or not delete the program, but escape out of the program, kill the program, exit with an error code instead. Right? Or okay, we'll go ahead and apply a different formula because it's a linear function, all right? The user supplied a bad password, so the way that we'll recover is by prompting the user again for the correct password. But if that happens 3 times, then we'll go ahead and quit out of the program. That kind of decision-making process is made at the user level, where you're writing the programs, not at the library level, where you don't have control, all right? Any questions so far? No? Well, that, yeah, go ahead.
Yeah, so you're making this so when you're coding for a program, you know the errors. But when you're coding for math and I do an error, I don't know, I'm not telling my program to set up an output for those errors. So how does that work? Like if I don't know the errors, like the enumerator errors, how can I make my own program to handle those errors? Yeah.
Well, through documentation. So if you're using a library that you didn't write, in the documentation it will say it returns an error code in the event of blah blah blah, and then you've got documentation similar to this, and you have to read through it and say, okay, well, 5 different things could go wrong when I call that function over there, and I'll choose to handle these 3. Those other 2, they're very unlikely to happen, so I don't care about them, right? But that was my decision, right? It wasn't the library dictating to me, no, you will have to do, we will quit on you if any of these 5 things happen. It's we'll report one of these 5 things or no error at all, and then you decide what to do. And the way that they communicate that is through documentation. We could come back here and say that on the header file here, and update the documentation. Returns on error code, right? See, what was it, root error in the event of an error, right? And then we could come up here and document this, that these are the possible error codes. So I'm going to do the tried and true. No, you're never a true programmer or developer until you've actually done at least one to do the documentation later. There we go. So of course you'd write it out in complete sentences and good English, right? Well formatted English. Right? So, but I just put it in a to do. I'll do it later. Right? All right, I'll let you guys do it later. Good question that it's through the documentation. Right? All right. Okay, then you'll get more experience in this in lab tomorrow, and of course in Hack on Thursday, where you do some error handling. This is a very short module because we do have our midterm coming up in a couple of weeks. So keep that at the back of your mind. That we do have a midterm coming up in the 9th week. This is the 6th week, so it's you still have several weeks away, but keep that in mind. We're going to go on to Module 7 on Wednesday because it is going to be a much larger module and it'll take about 2 weeks to get through it, which is going to be arrays and dynamic